Let's now summarize what we've discovered about transformations and see what happens when we need to combine several transformations for the same graph. We saw that addition and subtraction correspond to translations. Multiplication did two different things. If we multiply by a positive number, that corresponds to scaling the graph. If the number is negative, there's also a reflection. When we're parsing these things, we're actually going to handle scaling and reflection at the same time, because both of them involve multiplying a coordinate by something. Anything that's inside the function, so anything that we do to x before we apply the function, has a horizontal effect. So adding inside the function is a horizontal translation. Multiplying inside the function is a horizontal scale. Anything outside the function has a vertical effect. So adding outside the function is a vertical translation. Multiplying outside the function is a vertical scale. By inside and outside, we mean things inside the function are written inside the function parentheses. They're happening to x before we apply the function. And then outside the function is outside the function's parentheses. They're happening to the output of the function after we apply the function. And the thing that we noticed is that horizontal effects are backward. Adding a positive number translates to the left, even though the positive direction is to the right. Multiplying by a large number scales the graph smaller. And the reason for that is we need to go back from the input of our new function to the input of our original function. We need to go back from the value of x to the input of the original function. We haven't talked yet about order, but it won't surprise you that we just obey the order of operations, at least outside the function. When we're working on our vertical transformations, where everything works the way we expect, we follow the order of operations. Multiplication comes before addition. Inside the function, everything is still backward, so we reverse the order of operations. Inside the function, addition comes before multiplication. And it might become clear why if you think back, way back, to when we were taking the inverses of linear functions, or even when we were first learning how to solve linear equations. When we're solving a linear equation, we get rid of the addition first, and then the multiplication. When we're going backwards, we get rid of the addition first, and then the multiplication. Now, when we're working through applying the effects of transformations, we will usually work on the coordinates of some key points, rather than looking at the picture directly and actually moving it around. And in fact, when we're applying multiple transformations, we will usually not sketch the intermediate steps. In this example, I am going to sketch the intermediate steps, just so that we can see a little bit more of what this looks like. But in general, we'll just take the original picture, work on the coordinates, and go directly to the final picture. So in this example, we're given the graph of f, and we want to sketch the graph of y equals -2 times f of 2/3 x plus 5 plus 3. I don't want to do that in one step. What we're going to do instead is to take some key points on the graph of f and then apply all of those transformations to those key points, one transformation at a time, by thinking about what effect it has on the coordinates. Again, in this example, I'm going to draw the picture after every step, but typically we would only draw the final picture. So, on the graph of f, we have a point -3, 2. we have a point 1, 5, and we have a point 7, negative 1. I'm going to start with the horizontal transformations and then move to the vertical transformations. Our first horizontal transformation is going to be the translation. We see that we're adding 5 inside the parentheses. Adding 5 corresponds to a horizontal translation 5 to the left. So we're going to take each x-coordinate and subtract 5 from it, the opposite of what we see in the function. So negative 3 minus 5 is negative 8. 1 minus 5 is negative 4. 7 minus 5 is positive 2. And then we don't do anything at all to the x-coordinates. To see the result of that transformation then, we have a point at negative 8, 2, a point at negative 4, 5, and a point at 2, negative 1. If we connect those dots with straight lines, just like we did in F, we see the same shape, just 5 units further to the left. Next, we're going to deal with horizontal scaling and reflection. So for that, we're going to look at the coefficient of x inside our function. So no reflection because that's positive. The scale factor is the reciprocal of what x is multiplied by. So we're going to take each of our x-coordinates and multiply it by 3/2. So negative 8 times 3/2 is negative 12. Negative 4 times 3/2 is negative 6. Positive 2 times 3/2 is positive 3. And again, we haven't touched the y-coordinates, so we're just going to copy those. What does that look like? Well, we have a point at negative 12, 2. We have a point at negative 6, 5. And we have a point at positive 3, negative 1. Connecting those dots, we see something that's similar to the orange shape, but more stretched out. It got bigger horizontally. Yeah, that makes sense. 3/2 is bigger than 1. Okay. Next, we want to take on vertical scaling and reflection. So we're going to look at the number that f is multiplied by. We're moving from horizontal to vertical now. We're thinking, okay, we're ready to apply f. We did that, and now we're moving on to the vertical. So here we're multiplying by negative 2. The negative sign means there's going to be a reflection. The graph we get next is going to be somehow upside down. And the 2 part tells us that it's also going to be twice as tall. So it's going to be upside down and twice as tall. We'll handle that at the same time, thinking of it as a factor of negative 2. We'll multiply each y-coordinate by negative 2. So 2 times negative 2 is negative 4. 5 times negative 2 is negative 10. Negative 1 times negative 2 is positive 2. And now we didn't touch the x-coordinates. The x-coordinates are going to stay the same. So let's see, what does that look like? We have a point at negative 12, negative 4. We have a point at negative 6, negative 10. Don't quite have room for that on our graph, but that's okay. We'll estimate it. And we have a point at 3, positive 2. Connecting those dots. Okay, that looks like the gray shape, but turned upside down and stretched out vertically. So far, so good. All that we have left is this vertical translation. And for that, we're going to look at this number that we're adding outside the function. We're adding 3 outside, so we're going to translate up by 3. We're going to add 3 to each y coordinate. So -4 plus 3 is -1. -10 plus 3 is -7. +2 plus 3 is +5. And again, we haven't touched the x coordinates. So what does our final graph look like? And this graph is our final answer. Well, -12, -1, -6, -7, and +3, +5 are our points. We connect those with straight lines, and that's our final graph. This is our graph of y equals -2 f of 2/3 x plus 5 plus 3. And we can actually spot check this, right? Because this point down here, we have when x equals -6, y equals -7. If we plug that in, -2 times f of 2/3 times -6 plus 5 plus 3, well, that's -2 times f of 2/3 times -6 is -4, so -4 plus 5 plus 3. So that's -2 times f of 1 plus 3. Looking at this point, f of 1 is 5. So -2 times 5 plus 3, -10 plus 3 really is -7. So if we actually take the x coordinate of one of our points and plug it in and do all of the arithmetic in a forward direction, we really do end up with the number that we got for our y coordinate. With a toy function like this, where really all we know about f comes from the graph, if we made a mistake somewhere, we might just get stuck. We might just not be able to evaluate any further. In a real function, we might be able to evaluate but get really ugly numbers, or we might be able to evaluate and just not get the point that we thought we would if we've made a mistake somewhere. Now, one thing I want you to notice in this order, when we were doing the horizontal steps, we didn't touch the y coordinate. We worked on the x coordinate only. And then when we were doing the vertical steps, we worked on the y coordinate only. So when I was telling you the order, I didn't say that horizontal comes before vertical. Horizontal doesn't have to come before vertical because they don't affect each other at all. It wouldn't actually make a difference if I worked on the y coordinates first and then worked on the x coordinates. That said, we always do the horizontal parts first because what we're thinking is things happen to our input, then we do f, and then things happen to our output. So the logic of the situation says that we should deal with the horizontal stuff first, even though mathematically either way would work out the same.